Properties of colloids, Brownian moment. When colloidal solutions are viewed under a powerful ultra microscope, the colloidal particles appear to be in a state of continuous zigzag motion all over the field of view. This motion was first observed by the British botanist Robert Brown and is known as Brownian movement. This motion is independent of the nature of the colloid but depends on the size of the particles and viscosity of the solution. Smaller the size and lesser the viscosity, faster is the motion. The Brownian movement has been explained to be due to the unbalanced bombardment of the particles by the molecules of the dispersion medium. The Brownian movement has a stirring effect which does not permit the particles to settle and thus is responsible for the stability of salts. Charge on colloidal particles. This is very interesting, very important for your JEE NEET exams. Direct these positive negative charge salts will be asked. Colloidal particles always carry an electric charge. The nature of this charge is the same on all the particles in a given colloidal solution and may be either positive or negative. A list of some common salts with the nature of charge on their particles is given below. Must read this, okay? Positively charged salts are hydrated metallic oxides like Al2O3XH2O, CrO3XH2O, Fe2O3XH2O. Basic dyestuffs, methylene blue type, hemoglobin oxides like TiO2. Negatively charged salts are metals like copper, silver, gold, metallic sulfides As2S3, Sb2S3, CDS, acid dyestuffs eosin, Congo red, etc. Salts of starch, gum, gelatin, clay, charcoal, etc. They are negatively charged. The charge on the salt particles is due to one or more reasons, like due to electron capture by salt particles during electrodispersion of metals, due to preferential adsorption of ions from solution and are due to formulation of electric double layer. Preferential adsorption of ions is the most accepted reason. The salt particles acquire positive or negative charge by preferential adsorption or of positive or negative ions. When two or more ions are present in the dispersion medium, preferential adsorption of the ion common to the colloidal particles usually takes place. This can be explained by taking the following examples. When silver nitrate solution is added to potassium iodide solution, we are adding silver nitrate to potassium iodide, Cl. The precipitated silver iodide adsorbs iodide ions from the dispersion medium and negatively charged colloidal salt results. However, when Ki solution is added to AgNO3 solution, positively charged salt results due to the adsorption of Ag plus ions from dispersion medium. In simple sense, you can say, if you are adding excess silver nitrate, it will get Ag plus ions. If you are adding excess potassium iodide, it will get I minus. Okay, so Agi by I minus is negatively charged, Agi by Ag plus is positively charged. If FeCl3 is added to excess of hot water, a positively charged salt is hydrated. Of hydrated ferric oxide is formed due to absorption of Fe plus 3 ions. However, when ferric chloride is added to sodium hydroxide, a negatively charged salt is obtained with absorption of OH minus ions. Fe2O3XH2O by Fe plus 3 is positive, Fe2O3XH2O by OH minus is negative. Having acquired a positive or negative charge by selective adsorption on the surface of a colloidal particle as stated above, this layer attracts counter ions from the medium forming a second layer as shown below. AgI by I minus K plus. Where do the K plus go? Excess K plus, they will be surrounding I minus. This is called double layer. The combination of the two layers of opposite charges around the colloidal particles is called Helmholtz electrical double layer. According to the modern views, the first layer of ions is firmly held and is termed fixed layer, while the second layer is mobile, which is termed diffused layer. Since the separation of charge is a seat of potential, the charge of opposite signs on the fixed and diffused parts of the double layer results in a difference in potential between these layers. This potential difference between the fixed layer and the diffused layer of potential charges of opposite charges is called the electrokinetic potential, or you can say Zeta potential. The presence of equal and similar charges on colloidal particles is largely responsible in providing stability to the colloidal solution, because The repulsive forces between the charged particles having same charge prevent them from coalescing or aggregating when they come closer to one another.